Welcome to Renewable Energies, the last part one lecture. Let me start with an announcement. I'm not sure whether Samuel Ritzkowski is attending, is listening to the stream. I wanted to remind you of the teaching evaluation. Our Students' Council is doing this with a lot of effort, and it is very useful for the teaching quality here at the department. We have the best teaching quality by far in the entire university, and this is largely due to the efforts with teaching evaluation by our students. Now, let's have a quick look on what we did last time, because we'll continue on that now in this lecture. So we were discussing 2 weeks ago, we were discussing the design of the rotor blades of a windmill, and we found the Betz design. And if I go back, then you see that we found that the farther you go out, so it's actually this formula that you should see if I would switch to it. So I think now you see it. So it's this formula, which actually says, well, if you make a little approximation, then you see here at this point that it is basically inversely proportional to the square of the tip speed ratio. Well, and this chapter, and we started it last time, this chapter is concerned with losses, so with a non-ideal, with a real wind turbine. And we said that we have 3 different loss mechanisms. The first is drag, right? And we quickly derived a formula for that. I'll repeat it in a second. The second is tip losses. And the third is actually what we are discussing today in detail, namely wake rotation, so-called wake rotation. Let's quickly repeat what each of them is. So the first one was airfoil losses, meaning that in deriving the formula that I just showed, we neglected drag. But we know, of course, that drag has the more impact, the larger the velocity, the relative velocity of blade and wind, which means that closer to the tips, you expect the impact of airfoil profile, of airfoil losses. And we found a simple formula. I noticed that I didn't write down it explicitly, so I added it here to the script, and I also put a red rectangle around it. So, so here you see the power that you could get from an ideal windmill. So this was the power that you can get from an ideal windmill. So you see here the Betz coefficient. And now it is reduced by this quantity. So the efficiency of the airfoil has a very nice form. We deduced it entirely analytical. And you see it's just related to the tip speed ratio. So you see the higher the relative velocity of air and blade, the larger the losses, but of course, the better your profile, the larger the glide number, so which is the ratio between lift coefficient and drag coefficient, of course, the lower the losses. Next, we had a particularly beautiful phenomenon. Namely, we recapitulated that an airfoil, so we were quickly discussing the pressure conditions around an airfoil, and we saw that there is, of course, positive pressure, which means higher pressure than the surrounding pressure, at the bottom side of the airfoil, and there's negative pressure lower than ambient pressure at the upper part. And yeah, so this is the reason why there is lift, or this is at least one scenario on how you can look at it. But now we saw, well, what happens close to the tips, or at the tips of the wing. And we looked at this at the example of an airplane, and and then there's kind of this short circuit, so that air can directly stream from here to there, right? Of course, you could ask, why doesn't it happen here? Well, the reason is that the airplane is just faster than this process here, right? So this is the entire trick how airfoils work. So, and the consequence is that the lift coefficient of the air profile is actually not constant throughout the wing, but it goes, well, more or less to zero at the tip of the wing. And well, again, we found a formula, and I also put a red frame around it. Also nice and compact formula. Again, you see the tip speed ratio. Here you see the number of blades. Well, this factor here is just a combination of different constants. Okay, 2 of the 3 loss mechanisms. The last one is wake rotation. And well, we were discussing here with this formula how we got or how we calculated power. And of course we said, well, power is force times velocity. And this means that for a given power, and so you should remember that each ring, each infinitesimal ring of the rotor plane has to deliver a power that's as close as possible to the ideal Betz case, right? And so you can either achieve this by making the velocity large, or by making the force large. We know, of course, that close to the tips, this here is large, and therefore the force, parallel or in tangential direction, will be rather small. But close to the rotor axis, it will be the contrary. There, this here will be large, the force will be large, and the velocity is, of course, small, the blade velocity. And the problem is the following. The problem is that if the wind exerts a large force on the blade, then, of course, also the blades exert a large force on the wind, which means that the wind is deflected. So let's write that up. So a given power can be achieved either by a large velocity, blade velocity, or blade element velocity, omega times r, or by a large force parallel to the rotor plane, of course, right? So F parallel. So the first case is encountered close to the tips. So the closer you go to the tips, close to the tips, and the latter close to the rotor axis. Okay, yeah, and yeah, so the first case, is no problem, yeah, but the latter case implies that there is a large force also on the wind. There is a large force on the wind. Yeah, Newton's third law, actio equals reactio. No. So on the Zoom channel, somebody should switch off his microphone. There's constant noise, I think. So actio equals reactio. Okay, and this means the wind is deflected. The wind is, well, strongly, noticeably, whatever you want, yeah, is noticeably deflected closer, in the areas close to the rotor axis. In the areas close to the rotor axis. Why is this a problem? Well, remember what we said when we discussed the ideal case. There we said it is not possible to take all the wind speed, all the kinetic energy of the wind. Rather, we have to ensure that the wind moves also after the windmill. Yeah? Otherwise, the wind would clog the windmill, as ridiculous as it sounds. So we saw that a velocity component after the windmill reduces the efficiency. In the Betz case to 16/27. Now we find that there's actually an additional velocity component, and therefore we have to expect that the efficiency of the windmill is further reduced. Yeah? So let us write that up. So we found that, let's say, for the Betz case, that non-zero velocity components, trivial remark, of course, limit, non-zero velocity components of the wind after of the wind behind the rotor limit the efficiency. And now we see that there are additional components. Velocity components, namely parallel to the rotor plane. Yeah? And this means the efficiency is further reduced. Yeah? And this effect, once again, is strongest close to the rotor axis. Yeah? So this effect, and this should come out of the calculation. Yeah? So this effect is most pronounced close to the rotor axis. So that should come out of the calculation. Actually, we'll find two things here, namely that this effect has an impact, of course, on the power. So it will lead to a reduction of the power. This is what we just said. But it will also have consequences on the design of the blade, so on its geometry. So we'll find two things in the next chapter, which has the headline Schmitz Design. So that's 7.4, Schmitz Design. 7.4, the Schmitz Design. And the first thing will be that I introduce the this man to you. Yeah, I have a few slides. So this is not Schmitz, this is Hermann Glauert. Yeah, perfectly German name, but he was actually British. And well, his parents, they emigrated to the United Kingdom. Yeah, so they produced silverware, if I'm not mistaken. And he was actually not too happy about his German origins, in particular, of course, not during war times when he pretty much started his career. So he was also a distinguished mathematician, and his brother was also a famous scientist in biology, working in Australia. And well, Hermann Glauert, he wrote this book, which is still nice to read. I read a few chapters online and then decided to order this book. It's also available in digital form. It doesn't cost much. He wrote here this book, The Elements of Airfoil and Air Screw Theory. So you see that, so a rotor of a windmill in some sense is also an air screw. So much of what he worked out is also relevant for windmills. He's famous because of the so-called Glauert-Brundle singularity. And actually people for quite some time believed that this phenomenon of supersonic airplanes, so this F-18 air fighter, so at supersonic speeds, and you see this, this spectacular appearance where pressure is low, and if conditions are right, then the moisture condensates here. But actually, this is not the Brundle-Glauert singularity, because nature tries to avoid singularities. So the theory that led to the Brundle-Glauert singularity breaks, of course, down before the singularity would occur. Glauert, by the way, so you see he didn't get old, in contrast to his brother. And he died in an accident. So they were blowing up the roots of a tree, and he was hit by some fragment and died very early, unfortunately. And this here is Gerhard Schmitz. he did his PhD in Göttingen with Ludwig Prandtl. He knew all the figures there. He certainly encountered bits, of course. And, he was working on war times was also a part of this industry in war times. And after the war, he was he ended up in Rostock and in Halle, and then he was deported, or they put it friendlier. He was invited with his family to the Soviet Union in order to help to build up the science, academia there. It was quite successful apparently, and after 6 years or so, or 9 years, I don't know exactly, he was sent back to Germany and he became professor in Rostock. And there he wrote this paper, I can provide you a copy, that explicitly put down the Schmitz design, so the thing that we are dealing with today, and also established what's known as the Schmitz diagram. Interestingly, his two sons also became professors at the University of Rostock. And when I researched that yesterday, I was caught by the fact that on their official lists of the University of Rostock, they would say something about the confession of their professors. And so his sons, they are listed there as Roman Catholic. And so I was interested whether he was also, what his confession is, and there was none. Yeah, so he got a few prizes in the former GDR. So he was well respected by the regime at that time. And I think, it would not have been a good thing for him to practice his religion if he really had it. They were originally they come from West Germany, so a pretty Catholic region, so it's no wonder that, nevertheless, I found that interesting. Okay, anyway, back to physics, and not only stories around that. Let's say a few general words on what we are doing. Yeah? So the first thing would be to define what the Schmitz design is. Yeah, so this is the blade design according to Schmitz. Delivers the optimum geometry, of the rotor blades when wake rotation, as defined before, is taken into account. So now let's define a few things, and to this end I try to find here a figure. So this one here. So you see a figure that I just changed a little bit. You see the rotor of the windmill, and now you see that this wind is actually deflected, changes its direction. Well, I should have drawn these arrows a little bit smaller, right? That would have been even nicer. Maybe at some point I'll fix this figure. But what you see is that we have here this delta U for the wind direction, and also for the wind speed, of course. Yeah? And we'll try to quantify that. So, what the situation that we have is that the deflection of air at the rotor plates leads to a velocity component delta U that is antiparallel to the velocity of the blade elements. Yeah, and the velocity of the blade elements is u. Yeah, u of r, and yeah, so we can write it as u of r and use this unit vector here. So there's a tangential deflection. Yeah? And now our strategy is to derive the lift from momentum balance. So our strategy will be to derive lift from momentum balance. Yeah, and what we know is, of course, that far beyond the windmill, the velocity is v1, yeah, so as indicated here, and far behind it is v3, and then we can determine actually this deflection here. So far in front of the rotor plane, we have v1, far behind, we have v3, and the difference is delta C, and delta U is just a component of that. Yeah? And the difference is delta C. So just a figure to make this clear. So this one here. Yeah. Just vector addition, nothing has happened. Yeah. Yeah. So now the point is that that delta C, that this delta C can also be related to the wind conditions, yeah? So to the relative speeds here, and this is what we'll do next. Yeah, so the idea is to establish Yeah. So what we have is that so if we talk about the inflow velocity or the well, the inflow velocity exists, of course, only in the rotor plane, but we can, of course, nevertheless use the vector so we can, of course, add this. No. We can, of course, add this vector here to this vector here, and we would get this vector here, right? So this is the hypothetical inflow velocity far in front of the windmill. And the same we can do far behind the windmill, right? And in the plane of the windmill, so this is somewhere in between, this is then the real inflow velocity. I have also a figure for that. So it's this one here. Does it fit now? Yeah. So the inflow velocity comprises the wind and the rotor speed. The wind and the rotor velocity. Far in front of the windmill of the rotor, we have C1, as you see in the figure. It's just a hypothetical. There's no airfoil there, but nevertheless, of course, we can define this vector. And far behind, same comment, and far behind we have C3, as indicated here in the figure. And therefore, we not only have that V1, so what follows from here is, of course, that V1 plus delta C is equal to V3. And what we see here is we can also write that C1 plus delta C is equal to C3. Well, in the rotor plane, we have this velocity, we can call it C2, or actually most of the time we said actually it's just C. So we have C2. And now we argue in the same way as we did for the Betz case. So we say that C2 is just the arithmetic mean of C1 and C3. We'll later derive a formula that justifies this kind of, at least I hope so. But we work with this, certainly reasonable assumption that C2 is something in between C1 and C3, to be specific, the arithmetic mean. So let's also put this down. In the rotor plane, the inflow velocity is C defined as C2. And now the important point, similar to the Betz case, of an ideal windmill, of the Betz approach, we assume that C2 is the arithmetic mean of C1 and C3. Oh yeah, here's a misprint in my script. Just discovered. So now we want to try to find the lift force. Yeah? And we are actually not so far away from that if you look at this here carefully. Yeah, so we said that this here is the inflow velocity. And now remember that the lift force is by definition perpendicular on the inflow velocity, which means that the lift is parallel to this vector delta C. Yeah? So this is important. The lift force Fa is always perpendicular on C. And this means that Fa is in fact parallel to delta C. Yeah? Well, you can also understand this with different words. We know, of course, that the lift is caused by the deflection of air, right? And the deflection of air is, of course, just delta C. Yeah? So this makes a lot of sense. Yeah? Another way to see this, or to explain it, another way to understand this is to realize that lift is a direct consequence of the change of the momentum of air. That lift is a direct consequence of the momentum of air. And, well, what we see is which is, of course, parallel to delta C. Well, we also should admit that we neglected here something. Namely, we neglected drag. Yeah, we neglected air resistance. But this is fine here, because we said that the wake rotation effect, that this is most prominent close to the rotor axis, where the wind speed is small, and therefore also the drag is small. Yeah? So a remark here, so 7 remark, we neglect drag because wake rotation is only relevant where wind speed is small, where wind speed is low, and therefore drag is low. Yeah? Okay, let's continue and try to calculate the lift. So, considering that force is change of momentum, yeah? The lift is given by, or can be written as, well, dF equals delta C times the change in mass, right? So we take the derivative of the force, and force according to we take the momentum and take the derivative, and this is the force, right? But in this case, we have stationary conditions, so the wind speed does not change in time. Only the mass changes. Yeah, same argument as we made before. So this is equation 10. Yeah? And now we have to find an expression for this dm, the derivative of the mass element. Yeah? And to this end, another figure, actually pretty close to the figure that we have shown before. You see that it's actually pretty much the same figure than above. Yeah, so you see all the vectors that we had in this figure are also present here. I made them a little bit, well, less prominent, so that we only see the important ones. And, well, now the mass, the relevant mass, or the mass element, is of course given by this velocity component. Yeah, so this is the wind that goes through the rotor plane. This is the relevant quantity here. So let us write that down. So for dm dot, we use the air mass that flows through the rotor plane. That flows per unit time, of course, through the rotor plane. Well, actually, through an infinitesimal ring, yeah? Through an infinitesimal ring of the rotor plane, just in the same spirit as we did it for the Betz case. Yeah? And then, according to this figure, we find that this rate of mass, or this mass flow, is given by rho times 2 pi times r times dr. Yeah, so this is an area that we have so far, 2 pi r dr. And now we need a velocity, and this is this velocity v2, and the component that's perpendicular on the rotor plane. That's equation 11. So next thing would be that we calculate the power. Yeah? And the power is given by u times f, yeah? Where u is the speed of the rotor blade element. Yeah? So this means so the power for the ring, infinitesimal ring, under consideration is of course given by force times velocity, and therefore we have dP equals dFA, I should write here FA, times the sinus of alpha times r times omega. Yeah? R times omega is the velocity, and now dFA times the sinus of alpha. This is the component. Once again, we said that the lift is perpendicular here to this axis. Yeah, so it's perpendicular to C. Yeah, so the lift goes in this direction, but we need, of course, only the component that's parallel to the rotor plane. And now we have this angle alpha. Perhaps I show what I mean. Yeah, so we have here the rotor axis, and this is the direction of the lift force, so dFA, right? And then we find this angle also here, and this justifies here this expression. Yeah, so what you have here is the cosine of 90 degrees minus alpha. So that's equation 12. Okay, now we need a few more relationships between C and C1 and yeah, this V2 parallel. And what else do I need? Another one for delta C. So a few equations that we need in a second. A few equations that we can read from the figures, in particular from the one above, that we can read from the figure. So the first one would be that we have C equals C1 times the cosine of alpha 1 minus alpha. The next one is V2 perpendicular is given by C times sinus of alpha. Yeah, so in the same spirit then for equation 12, I think. And then we have delta C is equal to 2 times C1 times the sinus of alpha 1 minus alpha. Yeah, so which you can directly read from this so from this triangle here. So, and these are equations 13A to C. Yeah, so 13. So now we can start to actually calculate the power. So we use equation 10. Yeah, we use equation 10 and plug it in here. And yeah, and then we use all these equations here. Yeah, so yeah, so we substitute 10 and 11 in 12. Yeah? And what we then get is dP equals R times omega times rho times 2 pi r dr. Then V2 perpendicular sinus of alpha times delta C. And now we use equation 13, A and B actually, 13A and B. And then we find R times omega times rho times 2 pi r dr. V2, no, actually this I replace, so with 13b. So we have C1 times the cosine of alpha 1 minus alpha times the sinus of alpha. And then I continue here with the sinus of alpha times delta C, and delta C I replace with 13C actually. Yeah. So then we have here 2 times C1 times the sinus of alpha 1 minus alpha. And, well, this results in R squared times omega times rho times 2 pi times dr times C1 squared times, the sinus of 2 times alpha 1 minus alpha. Yeah? A little bit of trigonometry. So this is equation 14. Okay, well, now comes an interesting point. So we don't know, of course, here the angle of attack. So we don't know the alpha here. And now the trick is that we get it by asking here just for the maximum. So we derive the angle of attack by looking at the maximum power. And this is, of course, achieved when the derivative of the power is equal to 0. So 12, the angle of attack alpha, for which P is maximum, can be obtained by, well, of course, by dP over d alpha equals 0. So we demand that this is equal to 0. So we calculate this thing here, dP over d alpha. This is given by quite a few constant prefactors, r squared, omega, rho, and so on and so forth. But now the important stuff, namely the stuff that depends on alpha. So what we have is, just realized that I forgot to write down here sinus squared of alpha. Right? So, sinus squared of alpha. And then we have here this other part, right? And then, lengthy calculation, but trivial calculation. So I just make dots here. What we finally get is all these prefactors, and then 2 times the sinus of alpha times the sinus of 2 alpha 1 minus 3 alpha should be equal to 0. Right? And of course, the product is only 0 if one of its factors is equal to 0. Right? Probably this one won't be 0. That wouldn't make sense, right? Of course, this is not 0 anyway. So the only thing is that this sign here, well, why can't this be 0? Because then alpha would be 0, and we know if the angle of attack is 0, well, there is no lift. Yeah? So this part here should be equal to 0. So we can write that this is fulfilled for alpha equals 2/3 of alpha 1. And you can consider this here as the justification of using the arithmetic mean. Well, we kind of derived it under this assumption, so it may be a circular argument, but I think it's actually not a circular argument. So you can think about it. Now that's kind of important. So I frame it. And then another relationship that we need, namely we want to know something about alpha 1. So if you look at this figure here, then we can find that the tangent of alpha 1. So this here is alpha 1. And the tangent is of course this here. So the ratio of these two here, right? Okay, so from the above figure, we read that the tangent of alpha 1 is equal to V1 over R times omega. So the green arrow in this figure divided by the blue one. And this can be written with the tip speed ratio, capital R over R, and the tip speed ratio. So tip speed ratio once again. So lambda A is defined as capital R times omega divided by V1. That's equation 15 here, and this one here 16. Oh, I think we should have a quick break. Right, 5 minutes of break, I suggest. And we would just have a cup of tea or something. So see you in, well, perhaps just 3 minutes. So let's continue. We just had an interesting discussion via Zoom on the future of teaching in these Corona times. But we are dealing here now with windmills. We can continue the discussion about Corona in the question and answer session, if you don't have other questions there. Okay, so let's see. So we had an equation for the tangent of alpha 1. Yeah? I will not use this equation. I will only use it at the very end, and actually I will just say that I have an equation for alpha 1. And so what you see is that alpha 1 is a known angle. So what we now do is that we substitute the optimum angle alpha into our equation 10, and and then we would continue. Yeah? So we have now the optimum angle, and so we can indeed calculate equation 10. This is the this equation with the lift force, and actually probably I use actually equation 12 later in order to calculate the power. No, actually, I do it with equation 10. Yeah? So because we want to calculate now the lift force, and then we say the lift force that we calculate in this rather messy way, this lift force must be equal to the lift force according to the simple formula. You remember 1/2 rho times A times the lift coefficient, right? And from this equation we get a condition for the chord length, so for the geometry of the blade. Okay, so let's do that. A few more lines of lengthy calculation. So the optimum angle of attack, alpha, can be substituted in the equation for the lift. So this is equation 10. And then we get dFA is equal, as we said, to C dm dot. There's a misprint in the script, so the dot is missing there. And this is given according to equation 11 by delta C times rho times 2 pi times r times dr, and the perpendicular velocity component. Then we substitute equation 13b, and we get 2 times C1 times the sinus of alpha 1 minus alpha rho times 2 pi times r times dr, and the perpendicular velocity component. Now we use equation 13a in order to get rid of that velocity component. So everything else is just copied. 2 times C1 times sinus of alpha 1 minus alpha times rho times 2 pi times r times dr. And now C1 times the cosine of alpha 1 minus alpha times the sinus of alpha. And now we can collect a few of these factors and rearrange it a little bit. So we have rho times 2 pi r times dr, C1 squared, so you see this factor twice. And then we have the cosine of alpha 1 minus alpha times the sine of alpha 1 minus alpha. So you see a trigonometric identity will help there. And in addition, we have 2 times the sinus of alpha. Yeah? And now we use the fact that alpha is equal to 2/3 of alpha 1. Right? And then we see that we get dFA is equal to rho times 2 pi times r times dr C1 squared 4 times sinus squared of alpha 1/3 cosine squared of alpha 1/3, and yeah, that's it. Equation 17. Yeah. And now to what I announced. We demand that this lift force is equal to the lift force according to, well, the equation that is familiar, so that everybody should know about the lift. So the dFA of equation 17 must be the same than, or as, probably, as dFA equals rho/2 times lift coefficient times c squared times chord length times dr, the length of the blade element. And this results in an equation for the chord length. Well, what we get is, of course, the chord length of the entire machine, of the entire rotor. And now it depends on your decision whether you want to have 1 plate or 2 plates or 3 plates, which is the standard, or perhaps 4 or 5. So 3 is the standard, as I said. So we'll get an equation for the total chord lengths. So for the sum of the chord lengths of all the plates. So this results in an equation for the chord lengths, more precisely for the total chord lengths. T of R total, which is the sum of the chord length of the capital N blades. So, in other words, we demand yeah, okay, yeah. So, we write dFA equals rho/2 Ca times c squared, and then we have here the total chord length, dr, and now we replace C with C1. right? So why do we do so? Because C1, this is the wind speed far, or in this, so this is the, so the relative wind speed far in front of the windmill, and this is closely related, of course, to the wind speed far in front of the rotor plane. So this is the thing that is measured. So the wind speed in nature, this is what's measured, and therefore we replace it by at least the relative wind speed here, and of course eventually it will be replaced by V1. So we have rho over 2 Ca C1 squared instead of C, and then total chord length dr, and we have to use here this cosine alpha 1 over 3. Yeah? So this is according to equation 15. Yeah? So okay, so this is equation 18, and now we do what we said, namely that equation 17 must be equal to equation 18, which means that rho over 2 Ca C1 squared total chord length times dr times cosine squared alpha 1 over 3 should be equal to rho times 2 pi times r times dr C1 squared 4 times sinus squared of alpha 1 over 3 times cosine squared of alpha 1 over 3. Right? And you see that we can kill a lot of stuff here. So let's start here with the cosine squared. Then we have, of course, rho. What else do we have? dr, of course. Yeah, so must be the case. Then we have in addition C1 squared. Right, and I think this is it. That's it pretty much. Right? Yeah. Okay, what we get is that the total chord length as a function of r is equal to 16 pi times r divided by Ca times the sinus squared of alpha 1 over 3. Right? Nice, isn't it? And somewhere, yeah, so for alpha, just to remind you, for alpha we have actually this relation here, right? So this here is also known. So the alpha is not so undefined as you might think, in just looking at this equation. Rather, yeah. So well, let's make a remark. Yeah. Alpha 1 is given by equation 16. Well, this here is of course an important formula. Yeah. And this is equation 19. Equation 19. And of course, we see more if we plot it. So let's plot this thing here and compare it actually to the Betz case. Here. No? Well, and I have to say, I just like it. Yeah, so this is here what we got for the Betz case. And now if you look at this, right, and you compare it to what you see in nature, well, it's man-made, but what you see in nature, you see exactly we see exactly these profiles, yeah, right? So, okay, nice. Good, but we are not done yet. We want to calculate also the losses due to wake rotation. So far, we have now the Schmitz Design, yeah? But now we want to know also the losses due to wake rotation. So this is chapter 7.5. 7.5. Losses due to wake rotation. Oh, Jan. Thank you. This is why we have the Zoom meeting in parallel. Good. Losses due to wake rotation. Oh, how ugly. So what we'll do is to integrate our equation 14. Yeah, so we'll integrate the power. Yeah, so this equation 14 will integrate over R, over the area of the rotor. So we will integrate equation 14. And for your convenience, I just write it down once more. So we have r squared omega rho 2 pi dr times c1 squared sinus squared of alpha, and then we have sinus of 2 times alpha 1 minus alpha. Yeah? And then we'll try to arrange it such, we'll get a result, but we'll try to arrange it such that we have as a factor the power that's in the wind. Right? So you remember from the very beginning of chapter 6 that we said that the power of the wind is proportional to the cube of the wind speed. Right? And we'll try to find here another formula where we have the kinetic energy that's in the wind times a factor. In the previous chapter, this factor was the Betz coefficient, and now it will be the Schmitz coefficient. Okay. We'll integrate, yeah? In order to find the power generated by the windmill. Yep. We will, so then the result will, or should be arranged, will be arranged such that the power P, yeah, that P equals rho over 2 times pi times r squared times v1 cubed times, well, a power coefficient. Yeah. Okay, so let's do this little exercise. So we use the definition of the tip speed ratio, r times omega divided by v1. Then we use sinus of alpha 1 equals v1 over c1. Right, so if you look at this figure here, you get it from this figure or from this figure. immediately. What else? And then the optimum angle. Yeah, so we use that alpha is equal to 2/3 of alpha 1. Yeah? If we use this, then we get dp is equal to r squared times omega times rho times 2 pi times dr times c1 squared sinus squared of alpha sinus of 2 times alpha 1 minus alpha. And now we plug in all that stuff. I could have saved this line, of course. Yeah. And then we get rho over 2 pi r squared v1 cube 4 times lambda a, and then we have r squared divided by capital R squared sinus cube of 2/3 of alpha 1 divided by sinus squared of alpha 1 times, well, the normalized radius. That's equation 20. Yeah? And the only thing that needs to be done is to integrate this. Well, let's do that. Integrate. Well, and now I do actually nothing. I just write an integral symbol here. Yeah, so we integrate this from 0 to 1 over the normalized radius, and we have 4 lambda a r squared over capital R squared times the sinus cube of 2/3 alpha 1. And again, alpha 1 is known by equation, what was it? Equation 16, yeah? So divided by sinus squared of alpha 1 d over r capital R, yeah? So, and that's our final result. We don't do the integral, we are just too lazy. Actually, Schmitz did it, but the result is not very beautiful. We just call this the Schmitz coefficient, Schmitz power coefficient, right? So this is the power in the wind, power of wind. And this Schmitz coefficient replaces the Betz coefficient. So, of course, it would be nice to see that this coefficient here converges to the Betz limit if we go far away from the rotor axis. So, if we make lambda a very large, then this should converge to the Betz limit. I did this exercise numerically and produced this graph here. So here you see it. Yeah. So the green curve here, this curve here corresponds to this thing here. And you see, indeed, it converges to the Betz limit. Very nice. So, final point, the Schmitz diagram. This is actually where we put everything together, all these 3 loss mechanisms we put together. So 7.6, the Schmitz diagram. Yeah, and what we say is that for a real windmill, what we have is that the power should be equal to rho times pi times capital R times V1 cube, that's the power of the wind, times the real power coefficient. And the real power coefficient includes, well, of course, not only the Schmitz power coefficient, but also the losses due to drag and the tip losses. Right? So Cp real should be Cp Schmitz, which is a function of the tip speed ratio, times the airfoil efficiency, which is a function also of lambda A and the glide ratio, and then the tip losses lambda A, that depend on lambda A and the number of blades. Right? Okay, well, we can look at it. So I did this. Yeah. Here. So you see here on the y-axis the real power coefficient as a function of lambda A of the tip speed ratio, and I did this for the Danish windmill type with 3 blades. And you see it depends on the glide ratio, and so the better the glide ratio, the higher tip speed ratios you can afford. Right? What you see is that, if you have so this is realistic, this is ambitious here, I would say. Right? So what you can expect is a maximum power coefficient of 0.45 or so. And you reach it for a tip speed ratio of 6 or, perhaps here in between, perhaps 7. Now remember, this is so this tip speed ratio of 7, this is exactly what we have for a modern windmill. But I can go one step further and show you a graph for an existing windmill. This is an Enercon 126, which 5-7 years ago, this was the most powerful wind turbine, existing wind turbine. It's maybe still the most powerful onshore windmill, but I think it's discontinued for reasons that we can discuss next time. So what you see is on the x-axis we have the wind speed in meters per second, right? And the red curve is the power of the windmill. Yeah? Of course, if wind speed is low, then there's hardly any power. So this should go up like the cube of the wind speed, right? And eventually it will go into saturation when the capacity of when its maximum power is reached, right? So it can't deliver more than the maximum power. And one would pitch the blades such that this remains constant. And if the wind speed is really a heavy storm, then of course they would switch it off, so it would go down eventually here again. Yeah? Well, the more interesting curve for our purposes is the power coefficient, right? So the power coefficient, which is what we calculated here, right? And you see that when you pitch the blades such that you reduce its power, right? Then of course this has to go down, right? But for the region where it works best, right? Yeah. So if you look at the power coefficient, it is exactly what we calculated, or well, more or less exactly, right? So I find this result more than remarkable. Yeah, so if we include the losses, then we get actually what is realized technically. So if you compare this to photovoltaics, there's also an upper limit, a famous upper limit, which is the Shockley-Kaiser limit. And this is the thing that I'll derive in my lecture on photovoltaics or actually on solar energy. It's a little bit more general. This is the fact. This is the thing I'll derive in that lecture. And what one finds there is that the Shockley-Kaiser limit, so the theoretical limit that a photovoltaic cell can deliver, a regular photovoltaic cell can deliver, is something like a little bit more than 30% of the incident solar radiation. And what you can realize in the lab is perhaps 25% or so. And what you can buy to put it on your roof is perhaps 20%. So you see, for photovoltaics, one is pretty far off the theoretical limit, whereas here we are practically there, right? So the windmills that we have are pretty much, well, in a certain sense, the optimum that's possible. Okay, with this, I thank you for your attention, and if you wish, then you can meet me in 10 minutes or so. I have to switch off everything here and also clean it a little bit, yeah, so that the next who comes is not infected. If I would be infected, I hope not. And with this, good evening and see you next week. Thank you.